Okay, we're going to start off looking at how ions are formed. So let's take sodium as an example. So we can draw the electronic structure of sodium. So we write sodium in the middle, and we know it's got 2 electrons in the first shell. It'll have 8 in the next shell, which is the maximum you can fit in the next shell, and it has 1 electron left over. So this is obviously a group 1 element because it only has 1 electron in its outermost shell. Now if sodium loses that electron, which is what it wants to do, so it'll be left with an outermost shell of 8 in this case, then we would redraw it like so. So you still got the 2 electrons in the first shell, 8 in the next, and that's it. So it has a full outer shell of 8 because it's lost this outermost electron. But to show it's an ion, we have to draw it in brackets, and we put a positive sign to indicate it has lost an electron. So whenever you see a positive sign, it means it's lost an electron. And if we were to write the electronic configuration of sodium, for the atom it would be 2, 8, 1, and for the sodium ion it would be 2, 8, because it's lost that electron, and we again put that in brackets with a positive sign to tell people that that's actually an ion we're talking about. Now we can do the same thing with chlorine. In the case of chlorine, chlorine is a group 7 element, so it'll have an outer shell of just 7. So 1, 2, 3, 4, 5, 6, and that's the 7th electron. So it needs to gain 1 electron in order to have a full outer shell. And when it does gain that electron, we can redraw it. And the 8th electron we show as a dot just to show that it's come from somewhere else. Now it has a full outer shell of 8, but we have to again put it in brackets and indicate a negative charge because it has gained an electron this time. Whenever something gains an electron, it gets a negative charge. And so we can write out the electronic structure again for the atom. This was 2, 8, 7. And for the ion will be 2, 8, 8. And to show it's an ion, you put it in brackets with a negative charge on the outside just to show that that is now an ion. Okay, now let's look at how ionic compounds are formed. And the best example is between sodium and chlorine. So if we draw sodium again, and here is its outermost electron. Now we will lose this electron to chlorine this time. That's where the electron is going. So we'll draw chlorine here. So we'll use dots this time for chlorine. And that X represents that electron that's come over from the sodium. So now we have the sodium has lost its electron to the chlorine, forming a chlorine ion. So let's just get rid of this arrow here so we can get rid of that outermost shell. So now we have 2 ions. So the sodium has formed the sodium ion with a positive charge, and the chlorine has formed a chlorine ion with a negative charge. So these are now held together because of these opposite charges. So in the exam, make sure you use the phrase opposite charges instead of opposites attract. Okay, you have to have the word charges in there. So they're attracted due to these opposite charges. It's also important to remember that whenever you have an ionic compound such as NaCl, the charges must balance. So if we've 1 plus here, we must have 1 minus on the other side with the chlorine. Let's look at an example that's a bit more tricky. So if you have calcium, this is a group 2 element, so it is a 2 plus charge. And if we were to join that with chlorine, which has a negative charge like we saw before, well, these don't match. Okay, they don't balance out. 2 plus and 1 minus will not balance out. So what you need to have is 2 plus and 2 minus. Well, how are you going to do that? Well, all you have to do is rewrite it as CaCl 2. So now you have two chlorines. If you have two chlorines, that means you've got two negative charges because you've got two of them. And so now, if you were to write in the charges, you see this is 2 plus and this is 2 minus because now there are two chlorines. And now that's perfect, they balance. Okay, so make sure you understand that and you can balance an ionic compound. Here's one last example. If we have magnesium, which is a group 2 element, so it'll be 2 plus, and we add that to oxygen, which is 2 minus. Well, do we think these are balanced? We have to do anything? Well, they're definitely balanced. 2 plus and 2 minus are balanced. So all we write is Mg and O. The 2 plus and 2 minus cancel out, so we don't have to do anything funny there. Okay, so onto the next thing, which is ionic or giant ionic structures. If you want to draw a simple diagram to show or to represent an ionic lattice structure, it would be sort of like this. So it would just be a bunch of positive and negative charges alternating like this. Okay, so you can see all these positive and negative charges all stuck together. So we have these are attracted, these two are attracted, and they're attracted this direction as well. Okay, so these ionic forces work in every direction. And because they operate in every direction, it's going to make ionic compounds very strong. It's going to give them a very high melting point. They can also be dissolved pretty easily in water sometimes. So NaCl, for instance, will dissolve pretty easily in water. But that is not true of every single ionic compound. Okay, next thing, let's look at covalent bonds in simple molecules. So if we take hydrogen as the simplest example, so here are two hydrogens, and both hydrogens want to have a noble gas structure, so they both want to have a full outer shell, but they only have one electron. So this first hydrogen, it can share its electron, and the second electron can share its electron, and so between them they've come up with 2, and that's enough to have a full outer shell. So the first hydrogen, if you count around the ring, has 2 electrons, and if you count around the other direction, the other hydrogen also has 2 electrons, so that's a full outer shell for both hydrogens. Let's look at chlorine. So chlorine is group 7, so it'll have 7 electrons in its outermost shell. So we'll draw those with dots. 1, 2, 3, 4, 5, 6, 7. And the other chlorine also has 7 electrons, so 1, 2, 3, 4, 5, 6, and the 7th one can be shared. So if we count around both chlorines, we should come up with 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's fine. 1, 2, 3, 4, 5, 6, 7, 8. And that also has a full outer shell. So that one works. That's a good covalent bond. Let's look at something more difficult like oxygen. So oxygen is a group 6 element. And remember, we only have to draw the outermost shells in all of these diagrams. So in this case, the oxygen has 6 electrons in the innermost shell, so we draw those in. 1, 2, 3, 4, 5, 6, so it's sharing 2. And the other oxygen is the same. 1, 2, 3, 4, 5, 6. Okay, so if we count around those two oxygens, we should come up with 8 in both. So 1, 2, 3, 4 in the middle, 5, 6, 7, 8. That is a full outer shell. And if we count the other direction, 1, 2, 3, 4 in the middle again, 5, 6, 7, 8. Okay, so both of those oxygens have a full outer shell. We'll do one last more difficult one. So let's look at H2O. So that means there's one oxygen. So we'll draw that there. And there are 2 hydrogens attached, which we'll draw down here. So each hydrogen has 1 electron to donate, indicated by those little dots. And the oxygen has its 6 electrons on the outermost shell to work with. So 1, 2, 3, 4, 5, and 6. So the oxygen is sharing 2 electrons, 1 with each hydrogen. So if we count around the oxygen, we should find 8. 1, 2, 3, 4, 5, 6, 7, 8. And both hydrogens should have a full outer shell of 2. So we count around 1, 2, and 1, 2. Okay, so that's how you draw a dot cross diagram for simple covalent molecules. Okay, let's go on to the next thing. And let's look at covalent bonds in macromolecules. So the first one we can look at is diamond. And in diamond, each carbon atom is actually attached onto 4 other carbon atoms. So diamond is made of pure carbon, and all those carbons are joined onto 4 other carbons. So there are no spare bonds. All the bonds in carbon are used up. Because there are no free electrons, because all the bonds are being used up in these covalent bonds, it cannot conduct electricity. But it is very strong, and it's got a very high melting point, and is very hard because of all of these covalent bonds. If we then look at something like graphite, graphite is also made of carbon, but instead of having 4 bonds, instead of those 4 bonds, it only has 3 bonds with other carbons. Okay, so it's still made of just carbon atoms, but the difference here is that in graphite there are only 3 bonds for every carbon. And this means because there's this spare bond down here, there's a free electron. Because there's a free electron, it means graphite can conduct electricity. So graphite can conduct electricity, whereas diamond cannot. And the other thing is that you find graphite in layers, like sheets of paper, one on top of the other. Each sheet is very strong, but they're still able to flow over each other. So graphite can be used as a lubricant. It can be used instead of pencil lead in a pencil, because the sheets break away from each other very easily. Let's look at one more, which is silica. So sand contains silica. Each silicon atom is covalently bonded to 4 oxygen atoms. So there's your sulfur, and there are 4 covalent bonds between each sulfur and 4 oxygens. This gives it the formula SiO2, which is why it is called silicon dioxide. Okay, that's its formula. And that's the last one we're going to look at there. Now go on to the next thing, which is metals. Okay, so if you were to draw a simple diagram to represent the bonding in metals, it would look like lots of positive charges from the protons of the metal atoms, and they're all glued together thanks to the free electrons in between all those positive charges. So that's how you could represent the structure of a metal. Now if you have a pure metal, for instance copper, all those atoms are exactly the same size, so they'll tend to form very regular sheets, very regular layers like so. And this means they'll slide over each other pretty easily. Okay, and if they can slide over each other, this means the pure metal is going to be relatively easy to bend back and forth. Okay, however, if we added a different type of metal into this copper, for instance, we'll see that the new atom, because it's a different size, this is going to disrupt the layers in the metal. Okay, so see, it's not as neat as it was, like so. So you don't get the same layers, and because you don't have the layers, they won't slide over each other as easily. If they don't slide over each other, it's going to make the metal stronger. So alloys are usually more stronger than the pure metal. So an alloy is a metal mixed with one or more other elements, usually metals, but sometimes things like carbon. Okay, the next thing we look at are polymers. And there are basically 2 different polymers we need to know about. So the first one is the thermosoftening. Oops. And if they give you a diagram of a thermosoftening polymer, it would look like something like that. Okay. And a thermosoftening polymer is one that melts when heated, hence the term thermo meaning heat, softening to melt. So thermosoftening is a plastic, a polymer that will melt when heated. The 2 examples you need to memorize are polyethylene and polypropylene. They're the 2 examples of thermosoftening polymers. The other type of polymer is a thermosetting polymer. And this has a different diagram to be able to recognize. And this one has these cross links, like so. And those cross links make the thermosetting polymer much stronger, so it won't melt very easily when heated. So it's totally different than thermosoftening, just because of these cross links making the thermosetting polymer stronger. Now we have to look at the properties of polymers and how they can be changed. So the monomer, illustrated here, that the polymer is made of will affect its properties. So here's one polymer, and let's say it's a very strong polymer. You might use it for making fabrics, or you could have a different monomer like so. Maybe this is a very weak polymer, breaks apart very easily. So the type of monomer you use will affect the properties of the polymer, but also the conditions that the polymer is made under can also affect how the polymer is used. So if we take polyethylene as an example, you could have two different versions. Even though it's the same exact monomer being used, the different reaction conditions can lead to two different types of polyethylene. So you can have low density polyethylene or high density polyethylene. And so it's the same monomer chain, but the difference is there are different reaction conditions to make those two different types of polymer. Those conditions are temperature, pressure, and the use of different types of catalyst. Okay, so there are the three different conditions you need to remember that can affect how a polymer is produced and its properties. Okay, now let's look at nanoscience. So if they give you a question asking you what is the size range for something to be a nanoparticle, that size range is 1 nanometer to 100 nanometers in size. If it's bigger than that, it is not considered to be a nanoparticle. So that's the magic number you need to look out for in the exam. It is 1 nanometer to 100 nanometers. That's what a nanoparticle is. And these nanoparticles are really good because they have such a high surface area to volume ratio. Okay, they could be used as really great catalysts and things like that. There are some other uses besides catalysts, so they can be used in computers, in sensors, and in cosmetics. The thing about using them in cosmetics like sunscreen is that because the nanoparticles are so tiny, they can actually go through your skin and into your bloodstream. And sometimes people worry that that might cause some harmful effects. Because normally if you rub a cream on your body, the particles in the cream are too big to get through into your bloodstream. But nanoparticles, they're so tiny, they can actually get into your bloodstream. So we have to be careful about that. And the last thing to remember is that nanoparticles contain only a few hundred atoms. Okay, only a few hundred. That is the number to remember there. So nanoparticles contain only a few hundred particles. Okay, that's it for this video, and in the next video we will look at isotopes.